Yes, after going through the basic concepts of what is a grain boundary, what are various types of grain boundaries, we now talk about the strengthening phenomena which happens in metals because of grain boundaries, and we call it as grain boundary strengthening. We'll just see that how does this strength the how does grain boundaries help us in strengthening the material here, increasing the strength of the material. So we we have already said that when we talked about the basic concept of dislocations, we have said that okay, dislocations are problematic for the single crystals. That means they tend to reduce the stress required to plastically deform the crystals. That is why we find that you can have crystals which are dislocation free, but that's a bit tough to do. And what I referred at that moment of time was also that if you look at it, this concept of dislocation carefully, the dislocations themselves were not that problematic. The problem was the movement of the dislocations. And we said that you can block or hinder the movement of the dislocation by various methods. And if you are able to block the movement of the dislocations, which we can do by various methods, we can enhance the strength of the material. And one of the ways to stop the dislocation motion happens to be the provision of grain boundaries, or what I here refer to as strengthening by grain size reduction. Means you are trying to reduce the size of the grains. And if you remember my last discussion about grain boundaries, we said that if you are trying to reduce the size of the grain, so you can have a coarse grain material like this, in which the grains are quite large, or you can have a material which is very fine grained here. So in a fine grained material, the grain boundary area will be quite large, or grain boundary fraction that we call is quite large. So you have what we call as a coarse grain material and a fine grain material here. The size of the grains in a fine grain material is smaller as compared to a coarse grain material. That is what we say that we will talk about the concept of grain size reduction and how it helps us in strengthening the material. Okay, we said that the plastic deformation happens because of the dislocation motion, and if you are able to stop this dislocation motion, the stress required will be higher and the strength will increase. So what you observe here is that this is the grain boundary now between hypothetical two grains. We understand here that there is an edge dislocation which is moving on this slip plane. This movement of the edge dislocation, which is responsible for the plastic deformation, is also called as the glide motion of the dislocation. So what will happen is that this dislocation will start moving according to gliding from here, here, it will come here, and ultimately when it comes at this step, when it comes at this interface where there is a discontinuity now, because now the crystal is discontinuous. The next set of plane is not the same one. So the slip was happening along this plane which is continuous in a single crystal. But now it has encountered a grain boundary which is nothing but I can say it is a barrier. It is a barrier to dislocation motion. So the grain boundary here stops the motion of the dislocation. So because on the second part or the second grain here, so we have grain A and grain B. So a dislocation was moving in grain A perfectly along a slip plane, but now grain A has ended and the grain B is now oriented in a different direction, and it has a different it has a different slip plane. So you cannot have that this dislocation will jump to the second grain. It can jump if the boundary here happens to be a low angle boundary. So we already talked about low angle and high angle boundaries, or small angle and high angle boundaries. In the case the grain boundary happens to be high angle boundary, this dislocation will not jump from one grain to second grain. It will not happen. Whereas in small angle boundaries it may happen. So, but when I consider large angle boundaries, what happens is that this dislocation is now interrupted. The motion of the dislocation is interrupted, and that is what we said in our previous discussion, that you can impede the dislocation motion, and this will help us in increasing the strength of the material. So we understand that for high angle boundaries, dislocations cannot traverse through grains. They cannot move from grain 1 to grain 2. So they start piling up. So they start piling up at the grain boundary. So you find that dislocation pile up starts. So we have used another term, dislocation pile up, means number of dislocations start accumulating at each of these grain boundaries here. Okay. Now this phenomena has been well established by Hall and Patch, and it is a relationship which is called the Hall-Patch relation. This Hall-Patch relation, Hall and Patch are the name of two scientists from University of Cambridge who actually experimented and then developed this relationship, which says that a fine-grained material, the one which has smaller grains, is harder and stronger than the one that is coarse-grained, because the former means a fine-grained material here now, has a greater total grain boundary area to impede the dislocation motion. And this expression is famously known as the Hall-Patch relation, that is sigma y, the yield strength of the material, is equal to sigma naught, which is a constant, plus k1, which is a constant, and d to the power minus 1 by 2, where d happens to be the average grain diameter. So sigma naught and k1 are the constants. So as we understand here, that as you keep on decreasing the grain size, the strength of the material will increase. So a fine grain material will be stronger than a coarse grain material. But there is a catch here, that this equation is not valid for very large grains as well as extremely fine grains. And we will see that what happens once you start decreasing the grain size too much, because this equation, if it is valid without any minimum value of d, if there is no minimum value of d, you will find that you will have infinitely strong materials when you keep on reducing the grain diameter as small as possible, maybe nano sized, what we call as grains. So it happens to some extent, but afterwards the trend is reversed, and we call that as what we refer to as the inverse Hall-Patch relation. And we will see in the next slide what is the meaning of the inverse Hall-Patch relation. But before going to that, let us look at this expression which we say is the Hall-Patch relation, and how it is practically seen in the case of some of the metals here. So what we observe here is that when you plot yield strength versus grain diameter, so we are plotting here yield strength versus the root of grain minus d to the power minus 1 by 2. We observe here that as the grain diameter is reducing, the yield strength is increasing. So we are seeing here that we are plotting d to the power minus 1 by 2. So as d to the power minus 1 by 2 is increasing, or the grain diameter is decreasing, the yield strength of the materials is seen to increase. Same thing is observed here also. But we have what we call as inverse Hall-Patch effect also. Means that what you are saying here is that when you reduce the grain size, the strength will increase. So what we see here is a plot between grain size. So you have the grain size given here, plotted here in nanometers. So grain size plotted here in nanometers versus strength of the material. So in this case, we have said that according to Hall-Patch relation, less is d, less is the diameter, higher is the value of sigma y. So that is what you observe here, that when you find that the grain size is getting bigger here, the strength is decreasing. So here you have grain size larger. Further increase the grain size, strength decreases. You decrease the grain size, the strength is increasing. But this is valid only up to a midpoint, up to a maximum point, which we say is a crossover point. So after that what we observe is that you do not observe what we refer to as further strengthening because of grain size reduction. After that, if you further reduce the grain size, now that value is normally around in the range of around 20 to 30 nanometers. If you go beyond below that, we understand that the strength starts going down. So here you are referring to somewhere this working zone where you have what we call as super strong materials, and that is where we say super strength is achieved. But if you want to have super plastic materials, you can actually then go to further reduction in the grain size. So once you go beyond this tipping point, which we say is a crossover point of super strength, so below that value of grain size, the Hall patch effect is not valid, and the inverse Hall patch effect takes over. So this is the normal Hall patch effect, which says that less is the diameter, higher is the sigma y. This is the inverse Hall patch effect, which we say that when you reduce the diameter, the strength also reduces. But it happens for very small size of grains, that is in the nanometer range. For otherwise, for most of your metallurgical applications, we understand that Hall patch relation is valid. Okay, thank you.